Yeah, I'd like to talk today about a simple way of constructing randomized algorithms. And this is joint work with Sam McArdle and Nairo Berta. So in one kind of broad sentence, the kind of aim of our work is to look for early fault-tolerant algorithms for classical data. So what do we mean by this? By classical data, for the purpose of this talk, I'll just refer to any data that comes via a classical description. So this could also include, for instance, Hamiltonians if this is given to us in some classical format. What do we mean by early fault tolerant? So this term I think has already been used in some previous talks, but just to give some additional motivation, I'd just like to draw some kind of very hand-wavy pictures for a few slides. So we can look at a timeline going to the future, and on one side we have near-term algorithms, right? So these are characterized by the current limitations we have on kind of the devices we have today. And many of these approaches, for instance, might run many small quantum circuits. They might try and leverage some classical power. However, at least generically, they usually kind of lack runtime or success guarantees. On the other hand, we have fully fault-tolerant algorithms. These, of course, have much larger hardware requirements. They're often specified in terms of some query complexity with respect to some oracle. But within this framework, they do have runtime guarantees. However, they may also have some caveats which can cloud any convincing practical advantage. So one question we can ask is, to what extent can we bring these fully fault-tolerant algorithms closer to the present day? Or, phrased a different way, how hardware efficient can we make them? Right. Of course, these algorithms are constantly being refined over the years, and if you refine the query complexity of these algorithms, this is kind of like a proxy for reducing gate depth, right? So the answer is these are constantly actually being refined and moved towards the present day. However, if we really kind of lean into this direction and make this our main goal, we could also ask, for instance, how hardware efficient can we make these if we allow for some kind of potential even small dip in performance, right? So this potentially motivates searching for a third category of algorithms which may draw from these two regimes. And so this kind of potentially motivates searching for the so-called early fault-tolerant regime of algorithms. And the hope is that this will still lie above some classical boundary such that crossing this boundary will correspond to achieving some practical advantage. So this is what we mean by early fault-tolerant. And for the purpose of this work, we're going to try and achieve hardware efficiency or move towards hardware efficiency by trying to reduce the total qubit count of these algorithms. So the outline of the rest of the talk will be as follows. So I'll start by looking at some other approaches to algorithms. We can then look at our approach where we focus on reducing the qubit count, then present some concrete examples and some finishing comments about our setting. So to start, quantum algorithms for classical data traditionally might look something like this. So we're going to run some quantum circuit, of course. There'll be some classical preprocessing, some classical postprocessing. And there'll also be another element often where we'll need some way of incorporating or encoding the classical data into the algorithm. And so this is often done via some quantum data access model. And so the quantum circuit will make repeated calls to this data access model. So as an example, we can look at the linear systems problem. Classically, we might want to do something like this. So we are given some matrix A and some vector B, and we want to invert A and apply it to B. So this corresponds, of course, to solving the linear systems of equations AX equals B, find X. Quantumly, the state-of-the-art algorithm might be written something like this. So given a block encoding of A and given oracle access to the quantum state ket B, which encodes the classical vector B, find ket A inverse B, which is the quantum state which encodes the solution vector that we want. Now, the state-of-the-art approach queries some data access model, which is this block encoding, and it doesn't have any explicit dependence in the dimension of the solution vector, which is nice. However, it depends on this kind of condition number kappa and has kind of mild dependence on the approximation error epsilon. So it's logarithmic and inverse epsilon. Moreover, this only uses order log n algorithmic qubits. So this seems very nice. However, there are many kind of well-known caveats. So for instance, here we're returning a quantum state. So this is a different problem we're actually solving to the classical problem. Of course, if we want to read out the full vector, tomography would require, for instance, scaling in the dimension of the system. We've assumed that the vector B is given to us somehow as a quantum state. There's normalizations here, right? So the output is a quantum state. This is then normalized in order for it to be a quantum state. And lastly, there's this kind of data access model of block encoding. And so it turns out actually to implement this block encoding, one approach, for instance, using QRAM, if you want order log n gate depth each call, this then requires order n squared qubits to implement. Right? With trade-offs if you want kind of fewer qubits but more gate depth. So this is then kind of really asking us for a kind of totally different regime of hardware requirements, right? So instead of order log n qubits, we're now thinking of like order n or order n squared qubits. Right? As a brief note, of course, if A has some structure, there could be many techniques to reduce the overhead of this block encoding. So for instance, the so-called select and prepare oracles can give this to you if A is given as a sum of L unit trees. It can give it to you in order log L qubits and order L gates. However, this is still some kind of additional qubit overhead that in a kind of early fault-tolerant regime, one might want to kind of minimize. Moving over to other early fault-tolerant approaches, so recently a lot of these algorithms have cropped up, and I think one will also be presented tomorrow by Daniel, I think. So yeah, that should be really nice to hear about. So far, the early fault-tolerant algorithms have all been kind of in the realm of Hamiltonian-type problems, so ground state energy estimation, ground state preparation, and so on. And the majority of them follow a similar spirit, which is trying to trade circuit depth for more circuit samples. So reduce the coherent depth and run more quantum circuits. And again, most of them have a complexity measured by a time of running a Hamiltonian time evolution oracle. So this seems like a nice idea because there are so many approaches, for instance, to Hamiltonian time evolution. But for the purposes of really trying to shave down qubit count, we can kind of categorize these into two categories. So the first category, we're going to use more qubits, but these are kind of really nice refined approaches. And then the second category doesn't use any more qubits, but has, in terms of worst case error scaling, kind of a super logarithmic dependence on the error, or the inverse error. And so we could ask kind of, is there something kind of in the middle, something that doesn't use any more qubits, but has kind of better dependence on the error? So now we can move on to our approach. So the first feature of our approach will be similar to other kind of early fault-tolerant approaches. So we'll run many quantum circuits, each of them of small size. And the second feature will be that we'll try and remove this quantum access to the data, right? And we'll replace it with some classical data access model. And then we can ask kind of what classical data access model might work or might be interesting. So the intuition in our work is to think about matrices with structure motivated by physical systems. So we focus on matrices with a known Pauli matrix decomposition. And so classical access here will correspond to knowing the coefficients in the Pauli decomposition and their weight, which is the L1 norm of the coefficients. And the problem we'll kind of aim for is, given some function f that we're interested in, and the matrix A, we'd like to try and sample properties of f of A. And in terms of the methods we use, I'm sorry to say there's nothing kind of really new here. Like we essentially use previously established techniques, so sorry to disappoint, but they are really nice. So I'd just like to briefly summarize them. So there's some previous nice work from Earl and Kiana, which decomposes time evolution operators into linear combinations of Pauli gates and Pauli rotations, right? And this is a kind of interesting decomposition because it turns out that by increasing the number of Pauli gates and Pauli rotations, you can actually constrain the weight of this linear combination, right? And so this linear combination, of course, is equivalent to a probabilistic combination of gates up to some phase factors and some reweighting. And so the kind of core idea is to find functions with well-behaved Fourier approximations, right? Then essentially we can decompose everything into one big probabilistic combination, and then we simply just sample from these using previously established, well-known kind of gadgets kind of within the realm of quantum algorithms, and then randomly compile everything into one step. So more precisely, the problems we'll be able to look at are as follows. So we can essentially prepare the effect of f of a applied to some state phi, and look at the overlap with some other state psi. Or in the second case, we can look at some more general observables. And our claim of our main result is as follows. So given a Fourier approximation to f, given the Pauli decomposition of a, we can write down a sampling algorithm which will give us the two quantities stated on the previous slide. Specifically, we'll also need preparations, of course, of phi and psi, or in the second case of rho, and an ability to measure this observable O. And we'll be able to also, with this algorithm, write down the number of gates or the gate depth required, as well as a sufficient number of circuits to run in order to hit some error threshold. What these quantum circuits will look like are simply the kind of Hadamard test circuit and its kind of cousin. And this will apply controlled versions or anti-controlled versions of essentially Pauli gates or Pauli rotations. So what the algorithm will look like is something like this. We'll have a routine that will repeat many times. And each time we'll simply sample one string of gates from a probabilistic distribution. We'll run a Hadamard test with this controlled. We'll multiply or collect a single measurement statistic, multiply this by some number, repeat, average, and then it turns out this will give us the kind of quantity that we want. In the second case, it's something very similar. Now we simply just sample two strings of gates. We apply one controlled, apply one anti-controlled. Again, collect a single measurement statistic, multiplied by a number, average, and then we get the kind of quantity that we want. Okay, so this is kind of the general picture of how this works. Now we can look at some concrete examples. So in the case of linear systems, the function that we care about is the inverse function, right? And it turns out Fourier approximations of the inverse function have already been kind of widely studied, and so there's one that's kind of nice for our purposes. And so we can write down the complexities in this case. And we can see the main kind of goal is achieved, which is that we're using kind of logarithmic number of qubits with no additional kind of overhead. And the rest of the complexities will be something as follows. So we'll have some required number of quantum circuits and some required number of non-Clifford gates, which will essentially translate into the gate depth. And we'll see again there's some dependence on this condition number kappa, and the gate depth is polylogarithmic in the error, and also depends on this lambda, which was the Pauli weight, the L1 norm of the Pauli coefficients. Now, what happens when we compare this, for instance, to state-of-the-art approaches? The first thing we notice is actually these two algorithms are solving kind of two slightly different problems, right? And so it becomes a bit tricky in order to make a totally fair comparison, right? One thing we could at least do is try and look for a concrete problem and compare in this setting. So one problem that may be of interest for quantum algorithms is computing single particle Green's functions in many-body physics. And we see that this essentially amounts to, amidst all the kind of stuff going on here, there's a kind of matrix inversion going on, and we're essentially looking at some kind of overlap quantity in the way that I phrased earlier, with respect to the ground state E0. So for now, let's assume we can prepare the ground state E0 and kind of abstract a bit and look at the picture of preparing a kind of overlap quantity with an matrix inversion, which is not normalized. So on the left-hand side, we can write down our complexities. And previously, I had things divided also by the operator norm, but I just set this to be 1 for simplicity for now. And then on the right-hand side, we can start filling in the complexities for the state-of-the-art approach. We see, of course, the main aim, which is to remove the block encoding overhead, is, of course, achieved. So we're using kind of fewer qubits. And if we want to compare the depth, this is then going to depend explicitly on how we're going to do this block encoding and the gate overhead associated with this. However, we see that very loosely, it's kind of quadratically worse. If we think about, for instance, the select and prepare oracles, this gate overhead will be order L. So we'll have an L multiplying here. And then we'll have a kind of trade-off or comparison between the Pauli weight, lambda, on the left, and kind of order L on the right, which is the number of Pauli terms. Right? And in some cases, the number of Pauli terms can be very large and could be larger than the Pauli weight. And so there's kind of trade-off here. Now, on the right-hand side, we also need to still extract a number. Right? So we could either do this with incoherent sampling, in which case you recover a kind of 1/epsilon type scaling. Or, of course, we can do a more coherent approach with kind of amplitude amplification techniques, in which case we incur a kind of 1/epsilon type depth. And I've written 2 different error parameters on the left and the right, because there's an additional subtlety, which is that on the right-hand side, of course, this is giving us a normalized quantum state. Right? So then we need to kind of remove this normalization factor in the problem that we care about. And so this error parameter on the right would also actually have to be kind of scaled by this kind of normalization constant here. Additionally, if we care about this normalization constant, we're going to need to find it. So if we do a kind of full end-to-end comparison, we also need to account for the resources for the subroutine to find this normalization constant. Finally, as an additional note, if we're looking at this kind of problem of linear systems where we're encoding a classical vector into a quantum state, it turns out that these kind of Hadamard test schemes allow a kind of simple incorporation of an encoding of the classical vector into the algorithm at a cost of some classical preprocessing and some sample overhead. However, it will only use kind of one additional layer of gates. Moreover, this kind of classical preprocessing won't be so large if the vector, for instance, is sparse. So the main takeaways of this comparison is that, okay, the main goal was achieved. We have a lower qubit count. However, this comes at a cost of some up to quadratic overhead in gate depth, with some savings potentially if the Pauli weight is small. Additionally, there's an additional sample overhead if we're looking at incoherent sampling by some factor which can be as small as 1, but also can be quite large. And this will, again, depend on the specificity of the problem we have. So earlier we were looking at kind of computing ground state properties, and it turns out we can do something like this also with our approach. So given the kind of usual conditions for ground state problems, so given a lower bound on a spectral gap and given an initial trial state with good overlap, we're also able to, for instance, use our approach to give an algorithm to prepare observables with respect to the ground state. One function of interest here may be the Gauss function. However, there are many kind of different functions that people look at. However, this is kind of suffices for us, and this function, of course, approximately projects to the ground state for positive Hamiltonians. And the Hubbard-Satanovich transformation gives rise to a Fourier representation, so again, we can plug it into our approach. We can again write down the complexities, and so they would depend in general on the overlap, gamma, and the spectral gap, delta. And here I've actually omitted logarithmic terms, so there's kind of logarithmic dependence on the error in the gate depth, but this kind of O notation absorbs that. And this can be compared, for instance, to other approaches to ground state property estimation or ground state preparation. So for instance, there's this early fault-tolerant approach, and we see that the sample complexities are essentially equivalent if we're asking for a constant success probability in our case. And this has some calls to some time evolution oracle. So again, plug in your kind of favorite time evolution oracle and compare. But again, likely we're either going to see a trade-off of qubits versus no qubits, and then also L, so the number of Pauli terms versus the Pauli weight in our case, lambda. How am I doing on time mode? Okay, perfect. Yeah, I'd just like to end on two kind of brief comments about our setting. Right. So the first is that essentially in this talk, I've showed like a very specific way using kind of previous techniques of decomposing matrix functions into an epsilon approximate linear combination of unitaries, right? It's a very specific linear combination of unitaries. And by doing this, by sampling from the coefficients of this linear combination, we can sample properties of this function. Right, so one kind of direct question is, like, there are so many other ways, potentially, of decomposing functions into linear combination of unitaries. Can we do better by finding other decompositions, right? And the answer is, at least using kind of standard techniques and sampling in the kind of exact way that I described with kind of basic Monte Carlo sampling, we'd expect not to do any better than something scaling in the operator norm of f of a squared. Right? Of course, again, this is not a strict sample complexity lower bound, but it's kind of an intuitive picture that if we're exactly sampling from the coefficients of this LCU and recovering a kind of epsilon across approximation to f of a, then this is kind of roundabout as well as we expect to do. And if we rewind and check the complexities of our linear systems algorithm and ground state property estimation algorithm, we'll see that this is essentially achieved up to logarithmic factors in our approach. Another kind of closing comment is that here we've kind of discussed a different kind of data access model. And with any kind of data access model, we need to be careful about its power. So one kind of interesting note is that with Hadamard type test circuits, it's quite easy actually to sample properties of low degree matrix powers. Right? And so the properties could be, for instance, elements in the computational basis. So if the degree is low, there's kind of efficient classical routines to find this. And so this points to a kind of need to carefully specify matrix functions with this access model in order to seek quantum advantage. There's also the other immediate open question of whether or not there are quantum randomized schemes to sample properties of high degree polynomials, right, which classical schemes potentially wouldn't be able to do. So to conclude, we've presented kind of a simple class of randomized algorithms using kind of previous techniques in order to sample from functions of matrices when we start from, firstly, a Pauli decomposition of the matrix, and secondly, a Fourier series approximation to the function. The main feature is that this is low qubit usage, and the gate depth can be potentially up to comparable for some problems if the Pauli weight of the matrix is small. This also has a few different properties to state-of-the-art approaches. So for instance, our approach directly gives you a number at the end rather than a quantum state. And classical vector inputs can be kind of naturally compiled into the algorithm. And to end on some future questions, of course, we could always look for more functions and more applications. And one kind of big question is how to obtain this Pauli input model for different classes of matrices, right? So in general, we expect extracting the Pauli decomposition to be, of course, hard. But there is a question of, like, are there kind of specific classes of matrices for which this is efficient? And then finally, I think our complexity discussion showed how kind of intricate and problem-dependent comparing complexities can be, right? So I think in general, it could be useful to do some more fine-tuned end-to-end resource analysis for quantum algorithms. So with that, I'd like to thank you for your attention, and thanks so much. Yeah.
Hi. Thank you for the nice talk. I have a question about one of the last slides where you asked this question of classical sampling, this matrix power. So what was this lambda parameter there?
So lambda is the Pauli weight of the matrix you care about A. So in the Pauli decomposition, the L1 norm of the coefficients.
I see. So here the caveat is that somehow this scales exponentially.
In the degree of the power, yeah.
Whereas the quantum algorithm does not scale like that.
Yes, yeah. Well, yeah, a traditional quantum algorithm would not.
So what would be the the scaling of the quantum algorithm with respect to lambda?
With respect to lambda, quantumly, with a randomized approach, if you want lambda dependence, I can't think of something that scales better. So this is a kind of open question. There are, I think, other approaches that aren't kind of in this randomized framework where you can potentially look at high degree polynomials.
So then what would be the complexity of your algorithm for the same problem?
So this classical scheme I'm showing is actually just spoofing a quantum, which is it's classically simulating a quantum circuit. I can't think of a randomized quantum routine that, depending on lambda, which does better than this. But I think there are potentially other approaches to use quantum algorithms which don't necessarily depend on lambda, but maybe depend on the operator norm of A in order to solve a similar problem.
Okay, thank you.
Thank you. Can you please explain the kappa square dependencies that you get? Because I noticed that in sample complexity, the epsilon can enter in different ways, but kappa square stays as compared to kappa scaling of regular, like optimal LCU.
Sure, yeah, this could be seen in a number of ways. One is that, like, with sampling techniques, you get a kind of epsilon squared, so then the kind of the size of the object you're sampling, or you're thinking of like the variance of your estimator is gonna scale with the square of the operator norm of the function you care about. And so the function we care about in linear systems is the inverse function. So this is how the condition number comes in.
And do you feel this can be improved for randomized methods?
So one way you could refine this is if you add some problem dependency into this. So if we take into account what quantum state we're applying this on, because at the end we're just getting a number. So what I've specifically said here was if we're starting with an epsilon close approximation of f of a to some linear combination of unitaries, right? But this is not necessarily required, right? We could find just an approximation of f of a that's epsilon close when applied to the state, for instance. And then you might have dependence on, say, like, you know, the overlap with the state rather than of the
Thank you.
matrix in general.
Thanks for the nice talk. I don't have a question. I think I might be able to answer Andras's question. So on the classical complexity slide, you've got lambda to the power of 2 times d. I think if you did it using QSVT, then you just have that the cost of the block encoding is lambda. The number of block encodings you use is proportional to d, so you'd have like lambda times d. And then I don't know whether it's epsilon or epsilon squared on the bottom, but
All right. Let's thank the speaker again.